Hello, everyone. I will present our paper entitled Efficient Importance Sampling Algorithm Applied to the Performance Analysis of Wireless Communication Systems Estimation. The objective of our work is to develop a generic state-dependent importance sampling algorithm via novel stochastic optimum control formulation to estimate rare event probabilities that could be written in the form of an expectation of some functional of sum of independent random variables. We use our approach to estimate the outage probability at the output Amar and EGC receivers, and we also evaluate the outage probability in the presence of co-channel interference and noise. First, so estimating rare event probabilities is of paramount practical interest in communication systems, for example, calculating the outage probability at the output EGC and Amar receivers. Several works have proposed closed form expressions of the outage probability, but they are generally not generic. So the Monte Carlo method can be used as an alternative approach. However, it requires a large number of samples for small values of the outage probability and is therefore necessary to use variance reduction techniques such as importance sampling. So first, let's introduce our quantity of interest, which is the outage probability. It's the probability that the SNR falls below a certain specified threshold. This probability is generally very small, so it's considered as a rare event probability. So in our work, we calculate the outage probability at the diversity receives without co-channel interference, and this time the function G is the indicator function. And the second application is the outage probability in the presence of co-channel interference and noise. And this time the function G is the cumulative distribution function of the random variable x0, which is the useful signal. Now let's introduce some mathematical concepts. We start by the naive Monte Carlo method. So we consider n independent random variables. The naive Monte Carlo estimator is the mean average of the function G applied on m independent realizations of the sum of these independent random variables. We also define the statistical error, but we noted that our quantity of interest alpha is very small, so it's more efficient to use the relative error, which is the constant c divided by the square root of m alpha. And therefore, to ensure relative error equal to tau, c square over tau square alpha samples are required. Since alpha is relatively small, high number of samples m is required, and therefore high computational effort is required. And therefore, this has triggered the need for alternative method to the naive Monte Carlo simulations with improved computational efficiency, and various reduction techniques have been extensively employed to develop efficient rare event algorithms. So importance sampling is one of the most popular variance reduction techniques. Its idea is to introduce a new probability measure F tilde, which reduces the variance but keeps the expectation unchanged. The importance sampling technique consists on writing alpha in the integral form, multiplying and dividing by the new density function F tilde. So the integral still evaluates the desired probability, and the idea then is to simulate several realizations of xi with the new density function and average the new function G tilde, which is the original G times the ratio F over F tilde. And finally, the importance sampling estimator is given by this expression. Note that the optimal change of measure that minimizes the variance of the importance sampling estimator is given by this expression, which depends on our quantity of interest, which is unknown, a quantity. And the aim is then to propose a suboptimal change of measure that is approximately very close to the optimal change of measure and leads to a substantial amount of variance reduction. In this context, we will use the stochastic optimum control to find the efficient change of measure. So its idea is to introduce the evolution of this Markov chain. Instead of sampling xn plus 1 according to the original PDF, we perform a change of measure, such as given Sn, xn plus 1 is distributed according to a new density function depending on a parameter mu n. This parameter is a function of n and the sum Sn. And the aim now is to find the optimal controls that minimizes the second moment of the importance sampling estimator. We define some useful quantities, the cost function, which is the second moment of our new estimator, and the value function, which is the infimum of the cost function. And the question now is how to solve the minimization problem and to find the optimal controls in mu n. The idea is to solve it sequentially by going backward in time. And in the following lemma, we state the dynamic programming equation solved by U, which represent the main contribution of our work. And our algorithm is divided into two principal steps: the backward step, where we determine the optimal controls using the previous lemma, and then the forward step, where we use these optimal controls to determine the new change of measure, and finally we obtain our new estimator. Before showing our numerical results, we introduce our improved approach, which is called aggregate method, whose aim is to reduce the backward cost without considerably affecting the amount of variance reduction. And its idea to divide the sum Sn into B blocks and compute the controls for each block rather than for each xi. And therefore, we decrease the cost of the backward step without the price of increasing the variance. Note that we will use the hazard rate twisting change of measure, and we will work in a log normal setting. We compare our approach to the Monte Carlo method and to the other well-known importance sampling estimators in terms of necessary number of simulation runs in order to meet a fixed relative error toll, and in terms of the CPU time needed for to reach the relative error toll. So the first application, we consider an independent random variable, log normal random variables, and we obtain the following results. So we see from this figure that our approach requires the smallest number of simulation runs. On the other hand, the number of samples required by the naive Monte Carlo simulation increases at an exponential rate as we decrease the threshold, and we confirm that the importance sampling techniques outperform the naive Monte Carlo method. We also observe from the first figure that our improved approach require a larger number of samples than our original approach. And from the second figure, we observe that our proposed estimator is the best in terms of the competition time competition for small threshold, and as the event becomes more rare, the time gap between our approach and other important sampling techniques increases significantly. But for larger outage probability, the CPU time of our approach is not the best, but we see that our improved approach, the aggregate method, has improved this time. And note that we did not use optimal variables B of the aggregate method, so we expect that if we use optimal parameters of the aggregate method, we will get better results. Another possible experiment is to study the efficiency as a function of the number of antennas n for a fixed threshold, and we can see again that our approach is the best in terms of number of simulation runs, and for the CPU time, our approach outperformed the other approach as the event becomes more rare. And also we can study the efficiency as a function of the tolerance, and similar results are obtained. We see here the improvement of the CPU time when we use the aggregate method. And now we move to the second application, which is the outage probability in the presence of co-channel interference for SISO systems. We consider L independent random variables, and here we see similar results. Our approach is the best in terms of variance reduction. For the CPU time, we see that our approaches are the best for n greater than 9. We see the improvement of the aggregate method. The same for the tolerance. When we vary the tolerance, we get that our approach is the best in terms of number of simulation runs, and as the event becomes more rare, our approach is the best in terms of the CPU time. To conclude, we developed a generic importance sampling algorithm in order to efficiently estimate rare event quantities that could be written in the form of an expectation of some function of some independent random variables. Our approach is generic in the sense that it's applicable without any restriction on either the distribution of the univariate random variable in the sum or the expression of the function applied to the sum. And it was shown numerically that our proposed approach yields to a substantial amount of variance reduction compared to other well-known estimators. As possible extensions, we can optimize the aggregate method. We can also apply our methodology to assess the performance of much complicated wireless communication systems configuration. We can also consider the multivariate random variables when estimating the quantity of interest, and we expect that the backward cost will increase exponentially with the dimension. And to overcome this, we propose to use cheaper approximations method for calculating the control, such as neural network. These are our references. Thank you for your attention.